Good morning, Professor.
Good morning. All right. Good morning, everyone. Welcome back. So let's go ahead and start. We're going to continue with chapter on Milky Way. So we should be able to finish that chapter today, and that will give you everything you need to finish the assignments of the week. Just a quick reminder: next week, again, we have a holiday on Thursday, so we will have no class on Thursday. But we will have a class on Tuesday, and I'll try my best to finish everything, within 1 day meeting. We finish the chapter that we have. So for now, let's go back to this few slides back. I think at least one slide back. So this is where we stopped last time on Tuesday, and we were talking about the orbital motion in the Milky Way. So we have the galactic center and what we call galactic plane. Basically, then the disks are, you can think of, they are like this, right? So those spiral arms are like that. So then most of the stars are basically rotating like that in terms of the, let's say, along that plane, along that galactic plane. So most of them, you can see, are nearly circular orbits in the disk of the galaxy. And as we discussed last time, most of those stars are population 1 stars. That means population 1 star are the young stars that basically formed within maybe last billion years or so, and are the way we can recognize them mostly because they have more metals in their composition than population 2 stars that are much older, anywhere from 2 to 10 billion years old, and they have basically very little metals, right? Heavy metals, as inside their composition, and most of those are in a halo of our Milky Way galaxy. And you can see that in terms of the orbital motion of most of the population 1 stars are nearly circular, going around the galactic center. But for the population 2 stars that are in the halo, they have very sort of like, let's say, elliptical orbits and also very irregular. So those, another way we can differentiate between the stars from the halo and the stars from the let's say from the disk. All right, so then if we look at in terms of overall motion of the let's say stars around the center of the galaxy, and remember, so just like the planets go around our sun, and there's this rotational motion in our in our solar system. Very similar thing is in our galaxy as well. But all the stars are moving. You can think about all those star systems, like our solar system, is basically moving relative to the galactic center. And generally, what we have here is the closer the star is to the galactic center, faster it is moving. further it is, slower it is moving, or at least this is according to the Kepler laws. So we talked about Kepler laws. We talked about how the motion of the planets in our solar system follows this Keplerian motion, where Mercury is moving very fast compared to, let's say, Pluto. So the idea here is this should also be the same for our Milky Way galaxy. So this is the model in terms of the solid body rotation. Prediction is that closer you are to the star, to the galactic center, the faster it should be moving. Okay, so it says orbit if solid body, and you kind of have something like this, right? Because the idea here is they go around the galactic center. But one of the things we have here is that's not necessarily what we observe. What we observe is that some of the, let's say stars or clusters of stars are moving about the same speed or even sometimes faster than the stars that are closer. So that's something that is definitely is not, let's say, what our planets do relative to our solar system. So we have, two graphs over here where on the right side is the rotational velocity for the planets, as we would expect in terms of, distance, let's say the way it moves, right? So let's say with the distance, the speed decreases, but in our in our galaxy, it's a little bit different, and we're gonna talk about why that's the case. But in terms of what we have here this is what we call this differential rotation, where different parts rotating at different rate. So, for example, if we take the sun as the reference, which we always do, right? We have that the sun going at the speed of about 220 kilometers per second, okay, and going around the galactic center, which is roughly 8,000 parsec relative to the sun. So that means this distance is about 8 kiloparsec. Kilo, remember, stands for 1,000. Then it takes about 240 million years for the sun to go around the galactic center. So in a way, you can think of, like, let's say it's about 4 times for every billion years. So then we have about, our galaxy, it's about 10 billion years old, roughly 10, 12 billion years old. So then we can calculate that, I guess the sun has been around, let's say if it's about 5 times per billion years, and if it's 10 billion, so maybe 40 to 50 times it's already gone around the galactic center. You can see, right, the stars closer to the galactic center orbit faster, so their period is actually less. It's a smaller period, so they might go around in 100 million years. Closer you are, maybe in 50 million years, depends. But closer you are, generally the smaller the orbital period. That's why Mercury goes around the sun is much quicker than, let's say, the Earth does. And stars further out orbit more slowly. It makes time, it takes them maybe billions of years to go around the galactic center. All right, so using this information, interestingly enough, we can figure out the mass of, at least approximately, right, the mass of our galaxy. So the idea here is using the Kepler laws. If you remember, we talked about when in a binary system, we can figure out the overall mass of the system by looking at the distance, and how they're moving relative to us. How you have two stars kind of going around relative to us by measuring their orbital period and finding out how they're moving relative to one another, how long does it take. All of those things can allow us to basically find the mass. And that mass is not for, let's say, a single star. It was for the binary system. So that's something we can do. So that equation was, let's say that equation, let me kind of go back. Let me give you the equation. So the mass was equals to the distance a cubed divided by period p squared. So I gave you this equation. We talked about this last time, where on the left side, it's the total mass. Back then, when we were talking about binary star system, we said that this is mass of A plus mass of B, basically the sum of the two stars in the system. But here we can think about this, MA plus MB is the total mass of the system. And for us, it could be in terms of what's basically within this orbit of the like sun relative to the galactic center. So the total mass within that orbit can be easily calculated from a cube over p squared. All right, so using this information, then we can technically calculate fairly accurately what's the mass within the orbit of the sun, and then we can kind of approximate what's also the rest of the mass that is beyond the orbit of the sun relative, to the galactic center. But that's where a little bit of discrepancy, let's say we see some kind of discrepancy. We're going to talk about that. But let's see in terms of the simulation, it shows that let's say if combined mass was 1 billion mass, solar mass compared to, well, I guess simulation kind of stops here. So the idea here is more or less, it's just basic. Oh, there you go. So I just had to wait. And that's, let's say if it was 100 billion. That means the idea here is we can fairly accurately measure more or less what we should expect. That means how fast it's going, and the orbital period can give us in terms of, should this be 100 billion times solar mass, or 10 billion, or let's say 1 billion, because depending on how much total mass we have within that orbit, you could see, right, the speed more or less changes. All right, so now what we can approximate is that, the mass of our galaxy is roughly about 400 billion solar masses. So, but again, that's a little of, let's say, taking into account that we are using the Keplerian, let's say, motion. Now, one thing we have here is, if we try to then use, let's say, what we learned about Kepler laws and what we applied to our solar system, and fairly accurately to our solar system, would be represented by this curve over here. So this curve basically represents what we call Keplerian motion. So orbital velocity based on the radius. So further you are, slower you are moving. But that's not what we observe when we are looking at the Milky Way Galaxy. So you can see that graph is, kind of like all over the place. So you have, these are more or less the stars. You can see that the orbital period goes relative from left to right, and the orbital velocity goes, upward. That means, for example, this just means very close to the center of the galaxy. Then you are moving away from the center of galaxy. So you can say, right, 6,500 light years, or actually kiloparsecs, 6,500 kiloparsecs, 33,000 kiloparsecs, and so on and so forth. So here, roughly 50,000 light years, which is about 33 kiloparsec. Now, the idea here is, instead of seeing something like this, which basically the expectation were in the beginning, we see this curve, kind of like this. And you can see, right, those are the data points showing the velocity of some of the objects that are extremely far away from the center. That means basically the edges of the galaxy. And their velocities are, instead of being somewhere over here, it's actually kind of comparable to the sun, which means they are moving about the same speed, or some of them even faster than the sun. So the notion that, further you are, slower you'll be moving, experimentally cannot be verified, and it's actually our experimental data contradicts that. All right, so the idea here is, clear this. So you can see, right, if all mass were concentrated in the center, then the rotation curve would follow the modified version of Kepler's third law. And Kepler's third law was that period square was proportional to the a cubed. That was the third law, at least the proportionality. And then modified, it just basically takes into account some of the extra things. But we don't see that. So, and one of the explanation of that is dark matter. Okay, so that means what we have here is the mass that we think, like let's say composed of electrons and protons and things like that, that we can see. That means we can see all the stars and things like that, and we can measure their mass using their other techniques, like finding their distance and velocities and things like that. Doesn't account for all the mass that this data suggests. That means there is probably some other type of mass, we call it dark matter, that we cannot see, because what we have here is most of the type of mass that we have, like stars and planets and things like that, they are luminous. They either generate their own light, the stars, or they reflect other light, which are the planets and comets and moons and so on and so forth. So, but then it's possible that there are different type of matter that does not illuminate. So, but they, their presence is visible, sort of like, let's say, right, in the data. We cannot see them, but the data suggests that there are way more mass than our eyes can see. Sort of like, let's say, or basically what we can detect with our instruments. So that's what we have in terms of this. Dark matter is a type of mass within our Milky Way galaxy that are undetectable to us. Let's say in an optical spectrum, but detectable in, let's say if we look at the velocities, how fast they're moving in terms of those planets, those stars, right, on the edge, suggesting that, next to those stars that we can see are also objects that we cannot see, because the only way we can explain why this can happen is assuming that there are way more mass than we can, let's say, assume that there is from the optical perspective. All right, so now that's why it's not necessarily easy to get the mass of the Milky Way or mass of other galaxies, because of some of those type of uncertainties. But in any case, we can estimate that the total mass in the disk of the Milky Way is approximately 200 billion solar masses. That means, it's like 200 billion suns combined together. So like, let's say 200 billion solar masses. But there are additional mass in the extended halo, which are basically could be in the form of dark matter, that can be approximately another 1 trillion solar masses added to the overall, let's say, mass of the galaxy. Okay, so again, because we don't see that, the only way we see that from the experimental data that suggests that the way those stars are moving basically can be explained only if they are being pushed or pulled by other type of matter that is invisible to us. So then we can say that about approximately that 1 trillion solar mass is come from that invisible matter that we call dark matter. All right, so let's look at a couple of things about dark matter. So we have falls into two classes. So we have massive astrophysical compact halo objects, or WIMPs, so weakly interacting massive particles. Again, so it is really very difficult, right, for astronomers to come up with the explanation of what dark matter is. So I'm sure you guys heard of dark matter, dark energy. Well, we really don't know what those are. So it just to able to fit information, let's say that we know into the data that we get, we have to come up with this type of suggestions, right, towards dark matter, towards dark energy, because if we don't take into account dark matter or dark energy, then we're not getting exactly what we predict without them. So that's kind of the in a nutshell. That means we have to assume that there is something there because experimental data shows that. So there are type of particles that we call baryons. So for example, protons and neutrons, they are called baryons. So we can say that, okay, so those massive, so machos, right, massive astrophysical compact halo objects are would be baryons, like planets, dead stars, white dwarfs, black holes, and so on and so forth. And some evidence that these are the significant fraction, but not enough to explain Milky Way's dark matter. Okay, so then we have weakly interacting massive particles. So these are exotic particles from Big Bang, like neutrinos, like let's say photons, neutralinos. So the symmetry partners for bosons and fermions. So this goes kind of like a little bit more advanced stuff. So bosons and fermions are subatomic particles. So that means what we're doing here is, the particle physics right now is trying to explain that. I don't know if you guys heard of this Hadron Collider in Switzerland. There's a very massive particle, let's say, the system where they smash particles into another. So let's say they take protons and one proton to another proton, they smash them together. And what happens here is that they can, during that collision of two protons, they can generate another type of particle. That's what we call exotic particle, that basically is created from the energy generated by those particle collision, which is kind of like really insane, where you can only see that particle if really you smash two particles together, and that collision generates so much energy, so much heat, so that it gives birth to another particle, which easily, quickly after that, decays into something else. But still, those experiments show that there's so much more that we don't understand. There are things like Higgs boson, there are neutrinos and things like that that we still don't understand what they are. But I think it's a matter of time, maybe another 50 or 100 or 150 years. I think we will have a much better understanding of what we're dealing with. So in any case, this is very speculative because we really don't know at this point even what's dark matter is, what let's say dark energy is. I'll try to find some let's say a video that kind of maybe gives you a latest our understanding of dark matter and dark energy and black holes and things like that, and I'll post it on Canvas for you guys to see. So I think it's really fascinating that there's things that we can see and things we can't see, but they're there, and they affect basically the motion of the planets and stars and so on and so forth. In any case, so let's continue with looking at our Milky Way galaxy. So we pretty much covered most of the stuff except the galactic center. And galactic center is, by itself is very fascinating region of space because for us, it's very difficult to see because in an optical spectrum, it's almost entirely invisible to us because there's so much gas and dust that, and as we talked about before, right, gas and dust basically block all the light behind them. So, and you can think of like, let's say, all this region, right, is this very thick gas and dust that completely in an optical spectrum blocks everything, within that, those clouds and gas and dust. But we were able to find ways around that by making different type of, instruments, different type of telescopes. Optical or visible light does not go through those clouds of gas and dust, but radio waves, that means if there's something behind that, or let's say within that, they generate not only optical light or visible light, but they also generate radio waves and X-rays and gamma rays and things like that. So those type of lights, remember, are for example, our eyes cannot see infrared or ultraviolet or X-ray. We cannot see them, but we can create a telescope or a detector or something like that can receive that information and convert it to something that we can understand. And that's what we have. So there is what we call extinction by 30 magnitudes. Now, there's an interesting, let's say, concept behind this extinction. So extinction means that as the light goes, things like this. So let's say here's a star, and let's say this is you, or let's say it's me on Earth. So if the light comes in and reaches my eye, that I'm seeing directly what light generated in the star. Just like, for example, you see pretty much entire sunlight that sun generates, because there's almost nothing between us and the sun. Okay, there are almost no clouds of gas and dust that you can think of. But imagine this is a really far away. So let's say the distance is extremely far away, and when the light comes in, it encounters very large clouds of gas and dust. So when it goes through the clouds of gas and dust, then the photons of light, remember the light has particles we call photons. So because this cloud is so dense, it has so many hydrogen and helium molecules and things like that. So they absorb and remit, absorb and remit, absorb and remit. And what happens is that they get scattered so much that by the time you see something, there's only just a tiny, like let's say you can say, right, 1 out of 10 to the 12 photons reach Earth. That means 10 to the 12. I mean, that's basically a trillion. So imagine, right? A light sends you a beam of trillion photon particles, and you get only 1 by the time it reaches you. So that's why it's extremely difficult for us to see there, what's going on over there, because of this 30 magnitude extinction. That just means that extinction means that you're losing some magnitude of the light by the time it reaches you. Okay. Well, we cannot see in optical spectrum, but what we can do here, we can see in infrared, and we can see in X-rays and gamma rays, not with our own eyes, but with telescopes. So we have on ground, we have a lot of radio telescopes, and radio waves can easily go through because, radio waves are very large. So let's say if this is a cloud and there are particles there, well, radio waves goes around them. But for example, the visible is like such tiny, right? So it's going to then be absorbed and remitted in somewhere else. But the radio doesn't have enough energy. It's, it has a very long wavelength, so it can easily go around those, let's say, hydrogen particles and things like that in the cloud of gas and dust, and just easily go around and reach us without really losing much of its information. So that's why, for example, then infrared, X-rays and gamma rays and radio waves, even microwaves, those type of, let's say, radiation, the type of light is easier for us to detect using detectors, right? Because some, the most of the visible spectrum light, it doesn't make it through. All right. So anyway, so if we look through, toward the center of the galaxy, toward the Sagittarius, then what we see here is basically many supernova remnants and shells and filaments. Remember, supernova remnants means that there's either a neutron star, or they're just basically entirely the star exploded and just pretty much disappeared, just a little of raw materials here and there. Or maybe there's smaller black holes, because generally there are like different type of black holes. There are black holes where the star explodes and becomes a black hole. And there's also a black hole that always present in the center of the galaxies. Those are supermassive black holes. And for example, those smaller black holes that, let's say when the star explodes and we have a black hole, that black hole actually can eventually evaporate. So it's going to take many millions of years, but those black holes, if there's nothing for them to eat, so like, let's say, they will eventually evaporate and disappear. So we do see some remnants of that, right? So that means we see a lot of let's say dead stars, white dwarfs and planetary nebula and so on and so forth. So a very busy place, let's say, in that region, right, toward the Sagittarius A. This is now another, let's say, image that is suggests there are a lot of activities going on. This is another spectrum that again, it's invisible to us, but this is something that we can see. Sagittarius A, the center of galaxy. Let's see. Okay. So we see some arcs over there, and basically here another image suggesting that there's something at the center where we have a Sagittarius A, and basically from all of the observation and calculations, there's a suggestion that that is our center of the galaxy. That means if you ever find, let's say, use one of those phone apps, find the Sagittarius, you can even, ask the app to show you where Sagittarius A is, then that's basically where our center of the Milky Way Galaxy is. So Sagittarius A is the center of our Milky Way Galaxy in the constellation Sagittarius. And obviously we cannot see, but all the evidence points that it contains a supermassive black hole. Okay. Now, again, remember, black holes are, objects, celestial objects that we cannot see because the gravity for the black holes is so strong that they do not even allow the light to escape. But we can figure out that there is a black hole by the fact that whenever some kind of, let's say, a planet or a star gets trapped, in a gravity well of this black hole, it slowly starts eating all the materials from the star. And when it's doing that, it emits some radiation in this X-ray spectrum. So X-ray spectrum, whenever we see something in an X-ray, we see nothing there but some X-ray signature. That means we know there is a black hole over there, basically, eating some kind of, a companion star or something like that. But there's also a little bit of misconception where we think that black hole is just sitting there and eating everything. That's not true, because black holes are, let's say if right now we replace our sun with a black hole of the same mass as the sun, nothing will happen absolutely, except that it will be completely dark and we all will die. But in terms of the planetary motion, nothing will happen. The Earth will still go around that black hole in 1 year. All the stars, all the planets in our solar system will follow exactly, it's just because there will be no light, there will be no life, let's say, on Earth. Other than that, since there's pretty much, we have no life so far found in any of the other planets, they will be, more or less unaffected by that. Maybe, let's say, obviously the Saturn, let's say the rings will not be reflecting all that light, things like that. But other than that, if you have a black hole at the center of our solar system, replacing our sun with the same mass, it's not going to start eating all the planets. What we have here is there is this radius that we call Schwarzschild radius. We talked about that, right? Only when you go beyond that radius, then you get trapped. But that radius is only like kilometers, or something like that. So it's way, way smaller than, let's say, the orbit of Mercury or something like that. So that means none of the planets will be affected by that. All right. So then, in terms of what we have here is, right, by following the orbits of individual stars near the center of the Milky Way, because what we see here is there's a star that going around something. We don't know, we can't see what it is going around, but it's going around something because it's gravitationally bound to that, object, that is going relative to, which means, okay, if we cannot see what's there, but stars kind of go around that, that means, the evidence suggests that there's a black hole. They're going around the black hole. So in any way, so you can say, right, the mass of the central black hole could be about 2.6 million solar masses. That means, it's as massive as 2.5 almost our suns combined together. So most of those supermassive black holes are very large. And this is just experimental data. You can see, right? Taking the Sagittarius A, which is right there, we see that a lot of different stars sort of go around that spot. Okay, they orbit that particular spot. And the only thing we can basically suggest is that there is something there that gravitationally keeping those stars in orbit like that, just like the sun keep all the planets in the orbit. but we can see the sun, but the black hole over there keeps all those nearby stars going around, and technically it pretty much keeps all the stars in our galaxy going around relative to the center of the galaxy. All right, so here more evidence, right? So you can see there is a movie of that. So let's see. I want you guys to see in terms of the data. See, it's 1995, and it goes almost 10 years or so. Okay. So, and what we have here is, if we continue, we can see that they are basically going. So this 3 million solar mass black hole is not visible at optical wavelength, but again, it produces X-rays and little gamma rays, and is less than 10 AU in diameter. Okay, so it's basically about Jupiter, you know, let's say from Sun to the Jupiter, about that radius. So, but still, you know, the black holes are not, let's say, very massive, but they're not very large, but they're very massive. So it's a very small, right? Only 10 AU in diameter, but it is 3 million solar mass. So, and gravity keeping those stars in orbit pretty much depends on the mass. So that's why very massive black hole can keep a lot of stars in the orbit around it. By the way, I uploaded the PowerPoint slides for this in a PowerPoint format, so you guys can actually play PowerPoint and see all of the simulations. All right. So, so let me see, there's a question. Is it possible if a star becomes a black hole, would it be able to suck another star depending on the size? Yes, of course. So the idea here is, if, for example, if you have a binary system, so you have a star here and star over there. So let's say star A, star B. So for example, let's say star A is very, or like star B, right? It's a very massive, it's bigger, let's say, and it's a very massive star. And remember, so they basically go around the center of mass of the system. But if star B is very massive, and it can then generate too much, too much energy very quickly, and eventually collapse on itself and die and become black hole. So then basically replaced with the black hole. And it's possible that eventually, during their orbit, maybe something will happen or something like that. This star A can get too close, and they start sucking into, like, let's say, the orbit of the planet. Star A, and eventually slowly spiral into the black hole. Yeah, it happens. We can see the evidence of that, and most of the time, that's the way we can detect the black hole. Because if you have a region like this and there's a single black hole, you're not going to know anything, because it's just sitting there, not reflecting, not emitting, not reflecting any light, and you can just be sitting there doing nothing, and we don't know anything about that. But the only way we can figure out the black holes is in a binary system like this, because it doesn't necessarily mean the entire star basically is being eaten away by the black hole. Maybe just a little bit of its material goes, and it takes millions of years, sometimes even billions of years, for the black hole to eat a star. So it's not like something like, happens over the lunch or something like that. So it's something that takes a very, very long time. But still, even a little of material going into the black hole generates sort of like a residual X-ray radiation that we can detect. And we can say, okay, so there's like nothing there, but there's an X-ray radiation. That means it has to be a black hole. Again, could it be something else? Maybe, but most likely that's a black hole somewhere over there. All right, so that's about it, guys. So we're done with this chapter. So next week we'll talk about galaxies. So continue with that. Just a reminder that no class next Thursday. So we finished a little bit early today, so we're pretty much going to go ahead and stop, right? Because I don't want to, let's say, give you too much stuff that is not on this week's, let's say, assignment. So all of today's assignments material has been covered, so you should be able to go ahead and finish the assignment and the quiz. Any questions before we stop?
No questions, but thank you for the lesson today, Professor.
All right, my pleasure. All right, you guys have a good.
Thank you.
Good
Thank you,
rest of the
Professor.
week.
Thank you, Professor.
Take care, everyone. Bye bye.
Thanks, Professor.
Thank you.
Thanks, Professor. Have a good day.
You too. Take care.